Coming back to this diagram, which we have already discussed, we are actually going towards signal generation in NMR spectroscopy, how a signal is generated. So all these events that we are discussing right now, they lead us to a signal. So we have seen this diagram earlier. If B naught is 0, these nuclei, they are randomly oriented and they do not have any energy gap between them. But as you increase B naught, an energy gap is developed between the plus half and minus half spin states of proton, and you can see that some of them are aligned along the direction of B naught, others are aligned against the direction of B naught. This del E shows us how much energy you have to provide to make a proton or a nucleus jump from low energy state to a high energy state. So you have to provide radio frequency of such an energy that is exactly equal to del E. And you know that del E is directly proportional to B naught. So if B naught is higher, del E is higher, and it means that the energy of the radiation that you are giving, that must also be higher. So they all have a direct relationship. And on the other hand, B naught is also directly proportional to the Larmor frequency. So for resonance to take place, Larmor frequency has to be equal to the radio frequency. So if B naught is higher, Larmor frequency is higher, so you have to provide a higher frequency radiation to match it with the Larmor frequency. So all of them have direct relationship with each other. And then we saw that these nuclei, because they are precessing with a particular frequency which we call the Larmor frequency, some of them are aligned along the direction of B naught, that is in plus half state, others are aligned against the direction of B naught, that is in minus half state. But you do not have one nucleus in your sample. You have lots of nuclei, right? So what should we do to see them as a one unit? So we have this one nucleus that is aligned along the direction of B naught. It's pointing up. You can represent this with the help of this vector. This white arrow shows one nucleus. But as I told you earlier, that you do not have one nucleus. You have lots of nuclei. You can see the Cartesian coordinates, x, y, and z. This is y-axis, this is x-axis, and this is z-axis. Remember, when we draw these diagrams in NMR, z-axis is usually vertically pointing up here by default. Just like B naught, which we show pointing up. So in NMR, we keep this z-axis on the vertical axis, y-axis on the horizontal axis here, and this is the x-axis. So we do not have one nucleus, we have lots of nuclei. Some of them are pointing up, others are pointing down. So we have many nuclei pointing up, and we have many nuclei pointing down. B naught is in the direction of z-axis. These nuclei are pointing up and these are pointing down. Which of them are of lower energy? Those nuclei which are oriented along the direction of B naught, they have lower energy, which means these nuclei are of lower energy, plus half state, and these are of higher energy, pointing against the direction of the applied magnetic field in minus half spin state. Now, you already know from the Boltzmann distribution law that there always is a slight excess of nuclei in the alpha state. And which one of these is the alpha state? This one. This is the alpha state. And you will always have a slight excess of nuclei in this state, which means that these nuclei will be of slightly higher in number than these nuclei. And the magnetic moments of these nuclei, which are pointing down, they cancel the magnetic moment of these nuclei which are pointing up. But still, we are left behind with some nuclei which are still pointing up. So those axis nuclei in the alpha state, they have their own combined effect, and we show them with the help of this bold vector, bold arrow. And we call it M0. M0 means the net magnetization vector. And this M0 or this net magnetization vector, it helps us to see or to look at the whole system at a time. So this M0 leads to the NMR signal that we will see in a moment, how it leads to the generation of NMR signal. This is also known as the bulk magnetization vector. The position of this M0 is very important, because the position of this M0 on the XY plane or on the Z axis, that will lead to a different information about the molecule. We can change or control the position of this M0 with the help of the different pulses that we give, the pulse sequence. So it's very important to know the position of your M0 during the experiment, and that will give you a different. So M0 is very important, its position is very important in all NMR experiments. And this is the block vector model diagram that shows the Boltzmann axis. So it's the same diagram as I showed you earlier. This is the x-axis, y-axis and z-axis in which B0 is pointing. These are the nuclei in plus half state. These are the nuclei in minus half state. Here you will have a slight axis that you can represent as M0. Now, how does M0 gives you a signal, or how does it leads to a signal, or what is the effect of this pulse? As I told you just a moment ago, that when you give a pulse, you are actually disturbing this M0 from its equilibrium position. Equilibrium position kaun si hai? Z-axis. So you are actually disturbing M0 from Z-axis when you give a pulse. So what is the effect of pulse on M0? Right? M0 shows the combined effect of all the axis nuclei, the combined magnetic moment of all the axis nuclei, and it's always pointing in Z-axis. B0 again is pointing up, and now you give a pulse. So there are two things you should know about the pulse. One is the direction, and the other is the angle. In which direction you are giving the pulse, and at what angle this pulse is given. So the direction of this pulse, which is shown by B1. B1 shows the RF pulse. So you are actually giving a pulse in x-axis. You are giving a pulse B1 in x-axis, right? So this is the direction of the pulse. Now, according to left-hand rule, this M0 will move away from Z-axis and it will come down to the XY plane. See, this is the XY plane. This is the horizontal plane, x-axis minus x-axis, y-axis minus y-axis. And this vertical axis, z-axis and minus z-axis. This is the equilibrium position, and this horizontal plane is known as the xy plane. So when you give a pulse in this xy plane in any direction, this M0 moves away from z-axis. The direction of the movement of this M0 is determined through left-hand rule, and that states that if the thumb of your left hand points in the direction of the pulse, then M0 will move in the direction of your curved fingers. You can see here that B1 is in x-axis. So this is the direction of B1. M0 will move towards which axis? Y-axis. M0 will move towards y-axis according to this left-hand rule. So you can see here that this M0 has moved away from z-axis towards y-axis. It has moved towards y-axis, and this is, can be determined from the left-hand rule. So we are giving a pulse in the plus x direction. So this M0 moves away from z-axis and it goes towards the y-axis, the plus y-axis. Now, as I told you earlier, that there are two things important: the direction and the angle. So from the direction you can determine in which direction this M0 is going to move, but at what angle. So angle is also important. So if you are giving a 90-degree pulse, that means you are giving a 90-degree pulse in x-axis. You are giving a 90-degree pulse in x-axis. So it will take the M0 towards, it will take M0 from z-axis towards plus y-axis, and it will make it move at an angle of 90 degree. So from z-axis it will come down to y-axis, exactly on y-axis, because the angle between z and y is 90 degree. So from z it will come and lie exactly on y-axis, and this angle is actually the duration of the pulse. So you give a pulse to your nuclei for a duration that takes it from z-axis towards the xy plane through an angle of 90 degree. आप इतनी ड्यूरेशन के लिए पल्स दें कि ये इसको 90 डिग्री फ्लिप कराए. And if here you have the detector will see it and it will give you a signal. So usually the detector is on y-axis. If you are giving a pulse on x-axis, the detector is here on y-axis, M0 is here. You give a pulse, it goes down to y-axis. The detector is here to detect it. It will relax back and the detector will detect this M0 going back, and it will give you an FID. That FID is then converted into Fourier Transform signal, which we will see in the next slide. If you want to give a pulse for a duration that is double than the previous one, it will take this M0 from z-axis through an angle of 180 degrees to minus z-axis. It has moved through an angle of 180 degrees, but in which direction? In which direction? It went from z-axis to minus z-axis, going through plus y-axis, because we have given the pulse in x-axis. So it has moved 180 degrees, but it has moved through y-axis. So this is how this pulse B1 affects the position and the angle of M0 that it makes with the z-axis. Remember, z-axis is the equilibrium position. It is the position in which it is of lowest energy. So what you are doing by giving a pulse is that you are exciting these nuclei. You are exciting all these nuclei and you are disturbing them from moving away from the z-axis, but again they have to come back towards z-axis, because they would like to come back to their equilibrium position, and that is where they are the most stable. Right? So now we have come to a point where we can have the NMR signal, and you will see this in this slide. We have this M0 on z-axis. So you give a pulse that is the 90x pulse. What does this mean? A 90-degree x pulse. So it's a pulse which takes m naught from z axis through an angle of 90 degrees, and the pulse is in the direction of x axis. So it will take m naught from z axis through an angle of 90 degrees towards y axis. It's not stable here. It wants to go back to its equilibrium position, that is z axis. So you allow it to relax back. You give it some time and allow it to go back to z axis. And you already know that we have a detector here. So you get the signal when this m naught starts going back to z axis, when it starts relaxing back towards z axis. That is when the detector starts detecting it and you get an FID. So relaxation is a very important phenomenon also in this whole process. If you do not allow these nuclei to relax back, you might not have a signal. When it comes down to y-axis, it is right in front of the detector. When it is moving away from the y-axis towards z-axis, it's actually moving away from the detector. And that is when it moves away from the detector, the signal decays with time, and you get this decaying signal which we call the FID. Now it's a time domain signal because the signal intensity, it varies with time. So it's a time dependent signal, and it is of no use to us. We cannot extract information from this FID. So what we do is that we convert this time domain signal into a frequency domain signal through a mathematical operation which we call Fourier Transform. And here we have this NMR signal in this form, in the form of a peak, and this is the frequency domain signal. From here we can extract different types of information about the structure of the molecule. So now we have the NMR signal. All these events that we have gone through are involved in generation of an NMR signal. So I hope you have understood all the events.